now. And the floor is yours, Evan.
All right, let's see if I get my screen shared. Screen, you guys, a little inception here. You guys see my screen, my PowerPoint presentation?
Yep, we see it.
Yep. So my talk here is deep learning for basketball. I created a project using neural network to predict the outcome of basketball games. Basically, I wanted to do something with a neural network, and I was sports betting, so I figured that combined both worlds. So originally I'm from Marshalltown, so you guys are from Iowa, just east of where you guys are at now. I got my computer science degree from Iowa State in 2004, and then I got my master's from Georgia Tech. And the Georgia Tech one is all online, so when you guys graduate and want to go to grad school, that's an awesome way to do it. It's cheap, and you can keep working your job. By trade, I'm a .NET developer. I've been doing C# since 2004, and I got my GED in machine learning in 2019. So this is my family. This is 4 years ago. This is Jack Trice. My wife got inducted to the Hall of Fame, so that's the picture I use. So this presentation is based on the code I used before I made this course. A live project's from Manning. Right now it's not fully released, so it's $25, eventually $50. It just walks through how to do what I did, basically, and there's more instruction with that. And if you get into the live project stuff, they've got some pretty cool projects, and you do get access to a bunch of books when you do it. So overview of what I'm going to talk about. I'm going to introduce the project, and then as the guideline of my presentation, I'm using Facebook's Guide to Machine Learning. It's a blog post I'll send a link to that talks how they go about doing their machine learning projects, and it's similar across all of the big companies. They just have the best blog post about it with some videos. Their projects are vastly more difficult than what I'm doing. So when you go to their blog post, you'll see they'll do videos of how they decided to do what they wanted to do. And I can get into that more later. And then after all that, I'm going to show how I deployed this to the web using TensorFlow.js and how I made an Android app using TensorFlow Lite. So product introduction, I got my master's degree and I just want to do something with it. So I figured, let's do sports gambling. So I created a neural network to gamble and just kind of see where it'd take me. I used TensorFlow version 2, which is fairly new when I started. Everything I did was in a collab notebook. It was just faster than the PC I had, and it's really nice to keep their environment straight up there. And I know I wanted to put it on the web because I had a couple friends that wanted to use it, and just for giggles, I wanted to put it on the Android operating system. So here's Facebook's Guide to Machine Learning, and the link is at the bottom. And they break it down a lot better than I'm going to do, but that's just the general idea. Their main, I guess, tent post or framework is goal defining. You want to define what you're trying to do ahead of time. A problem you'll have with a lot of machine learning projects, you start moving the goalposts. You originally want to get, say, 75% accuracy, and you're starting to get 60, but you don't want to throw it away, so then you change it to 60. Well, that's not good. You decide what you want to do and how to define that success. Then the data gathering is next. With Facebook and a lot of the bigger companies, they'll have real-time data as well as existing data. My project's not that complicated. I do some real-time data, but I do some production data, but it's not live. So I can just do a nightly process to bring in the more information, where they're bringing stuff in almost real time. And then data parsing, got to make sure you have good training data, good testing data. And Facebook really pointed out that put an emphasis on model creation. Your first model should be super simple. That's your baseline. It could be something as easy as a decision tree. And then you can build from that. And if you do small incrementations, it's easier to debug what you're doing and to see if you're getting real results or not. And then finally, accuracy testing. So for goal defining for my project is just predicting the outcome of the game. I want to know the points. So I know that I need to do a regression versus a categorization. Your categorization is going to be, is this a cat or a dog? Where a regression is going to be an actual number. And then for me, success is I wanted to be 60% against the spread. Now for history, I don't have the spread, so I wanted to be within 5 points of the actual score. And I don't quite get those, but if you're 60% against the spread, you actually do make money in the long run. If you're less than 60, you're going to lose money, and there's no point in doing that. For data gathering, I did use, I want to do 10 years of games. So I needed the game results, I needed their teams, the conferences, and the spreads. As I mentioned earlier, spreads I couldn't get for anything past like a year or two, but everything else is readily available. I used ESPN.com and NCAA.com to get those data, or get that data. And the way I did it was I had a .NET app that would go out and just download the HTML. The NCAA website doesn't necessarily like people doing that, so there were some issues. So what I ended up doing was I would download the files and then do the manipulation. Because I believe if I called it 5 times, you'd get some redirect and they'd get mad at you. So I just made sure I downloaded and then I did all my manipulation. And then once I had the HTML, both of these sites have a pretty standard template of what they're doing. So I would just get a regular expression fired up and that'd give me all the games for that day. And then I have a regular expression to find the teams and the results and everything like that. As noted at the bottom, I did do it in .NET. I do have a current version on my desktop written in Java that does it, or I'm sorry, written in Python that does everything. But like I said, I'm a .NET developer, so when I have a problem, that's what I go to by default. So data parsing, in the real world, you're not going to have clean data. So you're not just going to get handed the data set, so hey, this is perfect, go ahead. The biggest thing I had a problem with was ESPN would never keep the team's names consistent. You'd have a team like St. Joe's, sometimes with apostrophe, sometimes not. Capitalization didn't stay the same. So I spent a lot of time cleaning the teams, and that was a giant pain. When I finally got to workable data, I had to remove teams I didn't care about. So when Iowa State plays Athletes in Action or whoever their first game is, that's not a real team in the Division I. I have no information about them, so I just wiped that game out. That doesn't count. And I also have to remove canceled games. And a couple years back, the Battle of Atlantis, I think, had wet floors. It was too humid. So that stuff like that's typical with machine learning projects. You need to know how to handle empty data, like null values, or no data at all. There's multiple things you can do. For me, I just got rid of them. They weren't that important to me. One popular way to go about it is to normalize or to average out the data. So if you're missing a score, you take all the scores and what's the average and put it in there. But you have to be aware that when you do something like that, when you make a decision, it's a bias you're introducing. And there's always consequences of biases. Some matter, some don't. But it's just something to be aware of when you are cleaning the data. And then I had to normalize the data. Since I'm using all numbers, I wanted to keep them equal. One of the values I used was the actual score, which could be 80 to 100. And then I also did standard deviation. So how many points you score more than the last game? Well, if that standard deviation is 5, your score is going to overpower that, and it's not going to matter. So you have to normalize that down so they're all on equal footing. So I have milestone 2 up. Now this this project here, this collab notebook, is what I used for part of the manning stuff when I was getting the teaching set up. So you'll notice that I'm loading their CSVs. So as I told you, I brought all the data in. I then needed to remove some games. So anything that didn't have a score, I dropped. And then I went in for the data that I wanted to use for that I thought was important was the score. What was it home team score? What was it away team score? I then went into breaking it down even further. So in my head, a team at home is different than a team away. So I wanted to know how they did at home versus away. So not only the score of the game, what's the average score when they're at home? What's the average score when they're away? What's the average score, or how's their defense at home? How's their defense away? Things like that. And in doing that, it kind of gave me a better idea of how the team played. But then I also need to take into account that I've got 10 years of data. The Iowa State team from 2015 is not the Iowa State team from 2018. So I then needed to break it down per year. So this next set is games per year. I finally went on, and here's the nonsense you get when you scrape internet data. This whole renames team is just taking the bad version and the version that I'm expecting. And as you can see, there's a lot of them. Clean all the names up. And so then when I get to this point, I know that when I see Utah State, I will have all of their data. I will not have a Utah State and a Utah ST messing up my averages. So as I mentioned a little earlier, the values I wanted was your average scoring at home, your scoring away, your defensive average at home, which means how many points you've given up at home and how many points you've given up away. On my personal model that I'm using, I then did a standard deviation of your home defense and a standard deviation of the away defense. Because I wanted to see if you would consistently give up 50 points a game, or if you gave up 25 points one game and 75 points the other way, because that matters. So that I brought in standard deviation. For this project, I kept it simple, so I didn't include those. And since I'm a .NET person, I absolutely got my mind blown when I saw how Python handles data, where instead of looping, you can do bulk order, like bulk manipulation, bulk math. So it's super quick. Now, in this example here, I have to iterate because I need to go by teams. But here I found the home scoring and then the home defense, and then using the built-in Python expanding mean. Do calculate scores. Excuse me. And then, as I mentioned in the data cleaning, you have to know what you want to do with null values. For me, because I didn't care, I just dropped it and moved along with my day. This isn't always valid for all projects, but for mine, it worked just fine. And I lost 3,000 rows. A lot of it was teams like playing JUCOs and things like that. And then I then saved the data to CSV. So then I wouldn't ever have to do this again. I could just keep going. So that is how I parsed the data. So the next part is model creation. As Facebook points out, and I mentioned earlier, you want to do something super simple to start. Something simple would be home team wins by 5 or whatever. Just that's your base. And any model you make has to beat that. And then you can make a slightly harder model. The next version would probably be like a decision tree or decision forest, where you decide how that handles it. And then you move on to the neural network. The reason you want to start with something before the neural network is neural networks are really hard to explain why they work. Where if you have a decision tree, you can follow down the path of the tree and decide how you got to that end result. But for me, this was simple. I was just going to do a neural network. There are obviously some pros and cons to everything. One of the cons was neural networks need a lot of data to train. So I wanted to keep the network structure pretty simple. I didn't want to do 50 layers with a ton of neurons at each level, because it just wouldn't train. Like it wouldn't work very well. And then once you have your first iteration of your neural network, you then want to go through and make changes. So do I add layers? Do I remove layers? How many nodes in each layers? What kind of optimizer do you want? What kind of loss function do you want to use? Things like that. But again, you want to start with a base and then you build out from there. So back to the code. Let me open up another one here. I have all these stored in here. So in my Manium project, they do milestones. So like the first milestone is data cleaning. The this milestone is creating the network. And for the network, like I said, I kept it really simple. I did 2 hidden layers, and then my output layer is 1. So I don't go too much into it, but a general neural network is, like I said, it's just layers. It's based on how our brains work and how it works in biology. And the idea is that each layer gives input that passes the next one. In a sequential model, it goes from the first layer to the second layer to the third layer. This 32 is a number of neurons in that network, and then dense means it connects to everything else. So these 32 connect all 32 of these, and then you finally get your output of 1. A neural network does a function approximation, so it doesn't actually give you, you're not going step by step and getting a value, it creates formulas. So when you put your data in, you'll get the network handles a formula and spits out the value. That's what makes it really hard to determine why it's happening, because it's just a bunch of random formulas and you don't know why. You can do it. There are a lot of people, a lot of projects trying to make it more visual. So you would send your network into this library and they go, okay, here's what your network looks like. You can get into these and see what your neuron equals. So just backing up a little bit, a neuron has a weight and a bias. So you can actually track those weights to see how they're moving, and you can graph them and see when they start to converge and things like that. Now, this input shape is the values I'm passing in. For this project, my values are home score, home defense, away score, away defense. So I pass in an array. The array then does the neural network magic and spits out the value I have at the end. So that's kind of the general structure of a neural network. I mean, there's a ton of resource online, but I can go into more if there's people have more questions at the end. So as part of the model, there's also an optimizer, and this just determines what equations used to find the global optimum. So there are, I think Keras had at one point, there's like 4 or 5, but it grows all the time. And it's just, you need to determine what you're doing and then determine which optimizer is the best. Keras's documentation does a pretty good job of explaining everything. And it seems like there's new variations always coming out. But generally, they're doing the same thing. Each one will have a benefit. So there's an atom optimizer, which was fine. And then they came out with, I'm not sure what they named it. It was atom something, excuse me. And it just gets there faster. It gets to your answer quicker. So it's things like that. You just find out your project and then read up on optimizers. This next part is the metrics I want to have. So when I get my result, I also get back metrics of, or I'm training my model, I get back metrics of what's happening. Mean absolute error, how far away you are, accuracy rate, and then mean squared error. And my actual loss function is mean squared error. So this tells me how far away from my answer it is, and the loss function then propagates backwards through each layer of the neural network and adjusts the weights and the biases to be closer. Typically, you'll use mean squared error. There are some occasions you'll use something different. But again, you just got to see what you're doing and see what your options are. Like I said, that's all it takes in Keras with TensorFlow to build your model. This is just sugar to show later. So once you have your base network, you then have to take your data and make a training data set, a testing data set, and a validation data set. You need to keep those separate, because if you train and test on the same data, you'll get awesome results. When you put it in production, you'll get terrible results. So you need to keep those separate. Something that didn't matter for me, but sometimes will matter if you have a time series, like a stock market or whatever, you need to do chunks from different periods. So I want to train on 3 months and then test on the 4th month. If time matters. For me, time doesn't. I didn't care what season was used. I generalized that all the seasons are the same, so I did nothing special. So there is a simple call that you can just create it using a sample, and that gets your 80-20 split. So you have train and you have test, and then you have validation is your third one. Typically, your train and test are 70-30, and then you pull 10% from combined if you're doing the validation. There are times where your neural network will do the validation. You'll have to have another validation within training, and that tells you when you're done. So instead of saying I'm going to run 50 iterations of my training, I'm going to run until validation's at an acceptable level. So that's kind of your training and test breakdown. Excuse me. And then I mentioned earlier about normalization, normalize the data, and then test. One thing to note, you need to normalize on your training data, because you should never touch your test data, because you should know no information about the test data. So if you start normalizing on all of your data, you're basically looking into the future and getting values that you don't have yet. So you got to make sure you don't do that. And then, like I said, in Keras, it's as simple as calling the fit method on that model I created. Passing your training data, passing your labels. An epoch is how many times you iterate through the data. Here I mentioned earlier the validation split. I use 20% of my training data to decide when I'm done. I don't need a bunch of messages. And then I had a print doc up above that just prints dots because I don't want to give a bunch of data. So that's your training. And then, as I mentioned earlier, the metrics that come back get put in this array, and you get information like this, which is your loss function, your absolute error, stuff like that, and you can dig into this. Typically, what you'll see is people will plot the epoch, which is your iteration, against your error, and you'll see something like this. Your training will eventually go down. If you train enough, you will absolutely overfit your data. And that means that you are very good at the training data. It will not generalize to real data that you haven't seen yet. And that's what you want to avoid. You need to have your model generalize to other data, so you can bring in the next season, you know how to handle it. And like I said, I'm getting better. My training's staying just about 7.25, 7.5 points away. Like I said, I wanted 5. I'm not going to get 5. I typically stayed around the 7.5, 7 point range. So that is, like I said, the simple model creation and how I broke out the data. Let me open up milestone 4 here. And like I said, Google Colab ties in with GitHub. I could keep this all in my Google Drive, but I wanted to version it. So I always go back to GitHub for everything. So as I stated earlier, I'm going to just cover this real quick. Neural networks will overfit if you keep training on them. It'll look like this. So when you see your training data keep decreasing, once your validation starts increasing, your network's overfit and it doesn't generalize. You don't want this. You basically have a worthless model if you're overfitting. And if you guys have questions, feel free to interrupt me, because I wasn't sure. If I'm not clear on something, let me know. So as I mentioned in the slides, you then do iterations. I did my default iteration. Now I'm going to jump through some hyperparameters. Now, most of these values are, it's more of an art than a science. I couldn't sit down and tell you, oh, you need 3 layers here because of X. It's try 2 layers, try 3 layers, and see what you get. So it's a lot of trial and error. There's a scientific library, SkyKit, that actually has what they call a graph search. So you give them an array of, these are my parameters for this, these are parameters for that, and they will do a grid search of everything you pass in and give you the optimal output. Keras doesn't have that. So you just have to manually do it. So like I said, so layers neurons and activation functions. The activation is how the neuron adjusts. With the ReLU, which is the one that I use, it's pretty straightforward. Then you get softmax and sigmoid. Like I said, you just got to try it. Read up on the documentation, see how they handle your data, and how it'll work. Like I said, Keras has fantastic documentation, and there are a ton of demos out there if you want to get an example of everything you want. Atom Max. So Atom was the stochastic gradient descent default, and then Atom Max is just a variation that just optimizes a little faster. So then, like I said, all I'm doing here is iterating through. I load my existing model, train it, give me the output. So my original model was 7.8 when I ran testing. So then I knocked down the neurons a little bit to 24, 12. A lot of times you'll see these jump like binary, or if you have a ton of neurons with a ton of data, you'll see 32, 64, 120. I mean, it scales up like that. You don't need to try 12 and 13 because you're not going to get that much of a difference. More training, and like I said, I just go through the activation function, so it's nothing that exciting. One thing you can do that I really like with Keras, which I use all the time, Keras does let you just straight up save it, and you'll save the entire model and you can load it later. So that's how I went through my model creation. And the next step is accuracy testing. So again, this is a pretty simple model. I could easily just compare the actual score versus what I expected. It's not that hard. There are harder things to test, and that's when you start bringing in more of your statistics background. A lot of it's area under curve. An example from the Facebook stuff is, will someone click on an ad? Well, if you just pick 0, that they're not going to click on it, you're going to be 99.999% right. So you can't use yes or no there. You have to figure out area under the curve. You start bringing in, more of your statistics and people that are way better at math than I am. For me, how I did that, I had a Google Cloud notebook set up where I loaded my model, and then I just ran it. So I would pick a game that just happened. LSU Maryland just went through. So I went and grabbed all the information that I had and then ran it. How did it work? Was it good? Was it bad? The problem with this interface here, I did this pretty late in the season, and it was in the NCAA tournament, and those games are crazy. And one drawback with my model that I am trying to figure out a way around, teams, really good teams play really bad teams in the preseason, pre-conference, and I need a way to determine a conference weight. So Iowa in the Big Ten scoring, winning games 50-40 is vastly different than someone like Duke winning 80-70. So I need to figure out how to adjust scores between conferences, because when I get to the tournament, LSU does not play the same people Maryland plays. So LSU's data doesn't match Maryland. So it's a lot harder to get that across. So for me, like I said, for accuracy testing, I just ran it. I'd make a guess, and I'd see how it happened. So that's, like I said, accuracy testing. One thing I need to bring up. So when I mentioned data collection, when I was running this last year, every Saturday, I would go and get the current week's games and update the team's current statistics. If this was, I don't know, if there's more pressure on this model, I would do it every single day. So I'd constantly have all the team's best information to feed into the network. So that was something that I forgot to mention, that's how I kept all my data up to date. So a model's fine, but if you can't get it off your computer, it doesn't add a ton of value. So I made a website don't DOS attack my website because it's hosted on Google and I'll have to pay for it. I made a website. So for example, let's do Big 12. Big 12, let's do Iowa State and Kansas. So visiting team and home team. So I take all of Iowa State's visiting or away scores and I get their values. And I take all of Kansas' home scores and get theirs. And I call it get prediction. And it tells me home team's going to win by 15. So in 2019, Kansas was going to blow out Iowa State at home. And just for some sanity check on my side, I listed the values I was passing in. Their scores, their defense. So Iowa State at the time was scoring 66 at home, but giving up 78, which is less than ideal. And their delta was 0.32. So that was their standard deviation from game to game. And here's Canada's data. One sidebar here. At the end of last year, I did a stretch of 14 games where I got 12 right and 2 wrong, which would basically make me a billionaire if I could keep that going. I got pretty excited about it. So one thing to learn, always backtest. So I went and back-tested the entire year to see how the model actually would work in 2019. And it just happened that right before I started running the tests, or right before I started my streak of 12-2, I lost 10 games in a row. So to kind of keep yourself grounded, anytime you change, you have to backtest. So if I add a new value, if I do a new calculation, a new model, I need to backtest to see if it's actually better once I find a model structure I like. So for this website, my next step here is web deployment. So I built my model using TensorFlow 2 and Keras. I need to convert that to a model structure that TensorFlow JS can handle. Luckily, people at Google are a lot smarter than I have, and they actually just created a converter. So you really import TensorFlow JS, you call it a converter, you save the Keras model, and you download it and you put it in your website. And that looks like this. So the actual code you get is this model.json. This really long line gives TensorFlow JS everything they need to calculate my value. So they use this, and then there's this bin file that tells them how to work. So that conversion made me be able to use this in JavaScript. So all I had to do was convert my array of input values into a tensor and pass it to the predict method, and I got my answer out. So right then I converted to web. So I have a JavaScript model that I can pass about. This obviously comes in handy when you want to put things on your website. The next thing I wanted to do, just for giggles, was Android deployment. So just recently, within the last 5 or 6 months, Google came out with TensorFlow Lite. And that's where they're trying to go with all of their mobile development. And because my model is just numbers, I only need to bring the interpreter. If you had a system that you wanted to learn as well, you would have to download the entire TensorFlow Lite application. I have a Raspberry Pi set up that does object detection. I need all of TensorFlow Lite to do that. For this, I just need the interpreter. And again, for converting, you just call TensorFlow Lite converter from Keras. You got your model, and then you save your file. And it becomes a database of sorts that you can call into. One thing to keep in mind, if you ever done Android development, you have to make sure your Gradle file does not compress the file. If it compresses it, it screws everything up and all of the math gets off. And then added the dependency. So for that, here is my Android app. And my asset is, so here's my model. And all you have to do when you get this, you import TensorFlow Lite interpreter. You create the interpreter, build your float array, and run the interpreter with your float, and then your output array, which is for me is going to be a single number, and then return it. And that's it. I have a working Android app that does exactly what the website does, which is exactly what my Google Cloud does. So that's a way to get your model distributed to everywhere. Google Cloud has a pretty good system for doing all of this. I've never gotten into it because this is a dumb project for myself, and I don't need 10,000 people using it and continuous integration and all that stuff. I basically made my model. I'm not going to change it. But there are some pretty good APIs in Google Cloud that will push all this out. So when I change my model in one location, it'll do the conversions and push it out. But again, I don't need that. It's overkill for me. I was going to show you the Android stuff, the Gradle. So, oh, come on. So I had to, again, do this HTML, do not compress, and then use Azure TensorFlow Lite. And then, like I said, you're ready to go. There are a ton of demos for putting machine learning on Android. So if you want to do something like this, you can go nuts pretty easily following someone else that's done it before you. So to take this further, I do want to finish the Android app. I was hoping by this basketball season to have a way for my phone to go get all of the information. So I'd go to ESPN.com, grab the spreads, grab the teams, do the calculations, and then have it on my phone. So that's just something I personally want to do. There is a new to me, I'm not sure how actually new it is. It's called gradient boosted decision trees. The idea is that you have a decision tree that you have a decision forest, I guess. You have a bunch of trees, and instead of doing a typical process to determine who's the best tree and which one to use in that ensemble, you use gradient boosting. Use stochastic gradient descent to decide which tree is the best. It's getting a ton of love right now, and there's a lot of people doing it. I've never done it, so I want to get into that. So that's something I want to try and just compare it against the neural network, see how it does. And again, just keep testing my app and get it better. So to wrap up, like I said, goal of definition, I wanted to beat Vegas. If I could beat Vegas, I'd be rich, and I wouldn't be sitting here talking to you guys. And there's tons of money in Vegas. They've got way better models and way better everything than what I could ever do. Then data gathering, like I said, I grabbed the data, used the internet, just scraping techniques, parsing. I showed that how to clean the data, do all the calculations, things like that. Get your model creation. I jumped right into neural network and anything else, and actually test to make sure you actually get it to work. So this presentation is on my GitHub page, which I think is linked in the meeting under Deep Learning Basketball. And here's all my information. Twitter's that, GitHub's that. I am on YouTube, nothing cool. I think I do 2 presentations. A blog I somewhat keep up. And here's my email if you need anything. I think my LinkedIn's also linked on the presentation. And then here's the Manning Live project. So is there anything else? Any other questions? Something I skipped over? Something that wasn't very clear?
Hey, I had a question as well about the materializing of models, right? So like when you're obviously just doing stuff on your own, it's easy just to try to get the best accuracy and whatnot you have. But when you're in like a business setting, right, you want to be able to get a model that is going to be able to say, take this to a manager and say, hey, this is something that's going to be productive, right? How do you kind of take it from that step of like kind of like a pet project where you can just see a certain accuracy, and say, oh, I can get 50% to saying, hey, this is actually going to better things, right? And this change is going to, be beneficial for some reason or another. Kind of how do you see that process going, right? Because I think that's one of the hardest things in machine learning is just the taking it from like a personal project where you've got, cool results of your own to actually figuring out something that you can materialize and generate into something that other people care about, right?
Yeah. So part of that's the goal definition at the very beginning, saying, hey, we're doing X now. If we follow this, we can do Y. It is hard. So there is there's some pretty good adoption with machine learning. but there are still some places that don't trust it, and it's hard to make that sale. I had a previous company that the CTO came out and said he didn't trust it in so many words. So I could never sell a black box like neural networks to that person because I couldn't explain easily why I made the decision. So if someone doesn't believe it, you almost have to just do like the decision trees, the gradient boosting, things like that to explain to them how you got that value. But if you have a manager that believes in it, you're just showing your accuracy, showing how you consider success is enough. So like if you're at Facebook, Google, or Microsoft, the people above you are bought in. They understand the benefits. And for them, it's just like, hey, we are now doing X. I can get you Y. And a lot of Facebook specifically, they do A/B testing live. So when they serve you an ad on Facebook, they've got 2 versions running. So they real time, with as many users as they have, can immediately show that this new model is better than the previous model. So, I mean, I don't know. It's kind of a roundabout way to say, just kind of tell them what you can do and then prove it. But again, it's very hard if the person doesn't have the initial trust that the model will do something. It's not just magic, and that it'll work long term versus just your little subset of data that you've been given.
No, definitely. I think that 100% makes sense. And I had another kind of question as well, too, that was a little bit different, is that, I think it's really easy to kind of start out with like a set of data, like you kind of talked about with like basketball data, and then kind of already know the goal of, hey, I want to try to see if I can't predict wins, losses, kind of whatnot, scores based off of that, right? But I think something, too, that's really, really common today, right, is a company that's saying, hey, we have 10 years worth of data. We have no clue what it all means. We have no clue anything that it could be, if it could be beneficial in any way. We would love you to be able to help us figure that out and try to make some value out of that. I'm kind of curious how you'd approach that, where you have maybe the beginning, you've got all the data at the beginning, but you have no clue what the ending looks like, and kind of how you would approach that to try to attempt to, find some value in it, despite the fact that it could be, like you mentioned, old. It could be just like really gross in terms of all the way things are formatted and whatnot, and how you can kind of work through that.
Yeah. So for a network, a neural network, you have to have good labeling. So you need to have your ground truth, I guess. So if you just have, let's just use picture, object detection, image recognition stuff. If you just have 1 million pictures, you don't get anywhere. You need to have 1 million pictures with their label attached. So if you just have pictures, it's going to take you forever to go label those. You can do what's called like unsupervised learning, which you don't have labels and it kind of groups them on your own. That's kind of a way to get a ton of data into a somewhat structured event or a structured data. I guess I don't know how you would say that. But it is hard. If you have junk data, it's tough to get good data, to get something good you can use. An issue that I'm at Corteva right now. The summer interns had an issue of trying to get, it was counting bugs, basically. They didn't have enough data. So then you have to like fake data. And then you get into an issue of, is your fake data good enough? And is it valid? So if I'm making images, if I'm just pasting a bug on something and it's not real, your model is going to learn off that really poorly photoshopped picture, and it's not going to work very well. Personal example I have an app that you take a picture of a fish and it tries to tell you what it is. I had bad data. I learned that anybody that took a picture of a really big fish had them in it. So my model was actually training on whether it's a human or not. So if I had a human holding a perch, it'd say, oh, that's a muskie because of the person. So you have to be careful with your data and what it's actually showing. So that's an image stuff. For like in the sports world, teams change. So if you are training a basketball model on the 80s NBA, they are vastly different than today's game. So it's not real data. I mean, it's real data, but it's not valid data. So it's one of those things where you have to use your domain knowledge to realize that I don't want to look at the bad boy Pistons to determine if the Golden State Warriors 2 years ago were going to win, because they're different. That doesn't work. So in training, you gotta have to throw that data away. There are a bunch of companies making a ton of money ensuring that you get good data. But yeah, it's one of those things. You just try and get the data in workable. And then, like I said, if you have a ton of data, you can do a network. If you don't, the network's not going to work. You got to find a different model, whether it's trees or whatever. But there are a lot of times they use you have to fake data. And an example, so I'm not sure you guys are into robotics stuff. Robotics use reinforcement learning to train a robot. Well, training a robot in the real world takes forever. So they make a simulated environment and train on that. So it's fake data, but you try and make it as close to real life, so then it'll generalize out to the real world. So a lot of it is, if your data's junk, how can I make what I have extrapolate out to more data? And it's not easy. And like I said, there's people who make a ton of money making it work. So there's not like an easy, do X, Y, and Z, and all of a sudden your old data is perfect.
I mean, I have actually two questions, but my first one was about having your model go into production. And when you do that, I was reading about things that happen like model degrading and model decay with the production data. So in this case, would there be any things like that that you've noticed that when you try running it on some data that is like really recent or the updated data based on certain games, that you see it performing differently? Or what do you think about that?
So I get it doesn't train different. For, like I said, this project, the model doesn't change. Like, if you had a harder model that changes over time. So if you're Target and you have a model to determine ads, you have to be aware that the model that is trained in February is not valid for Christmas season. So as far as like the decay of the model, the model never changes, but there are times where you have to be aware that your model doesn't work as well and adjust for that, if that kind of answers your question.
Yeah, that makes sense. Yeah, and I think especially in sports, it might be more so with things like if there's like a key player who's not going to show up for a game, maybe injury or something.
Yeah, and so like a lot of with sports, just teams change, like the world, how the game's played changes. So, back in the day, NFL was run. Now it's West Coast, play action, things like that. You have to be aware of that. Stock market. Monetary policy has screwed up the stock market something fierce. So if you have a model that worked in, mid-90s, it's a different world now. And that's just, like I said, you have to bring some domain knowledge to account for that, but be aware that your domain knowledge has bias in it, and there are consequences. A big bias that was brought up was Amazon tried to remove the first layer of their screening process when they were hiring people. Well, it turned out Amazon didn't hire very many women. So their screening process, their model, straight up removed women. They didn't have any women get through. So knowing that, they decided to use, their bias was, hey, let's do what we're already doing. You have to be aware of that. So for me, my bias for the basketball was, I think home and away matter. I need to be aware that that's my decision. The model doesn't tell me that. So if you try and make your model tell you what you want it to tell you, you're shaping it in the way you want it to work versus, hey, let's let it run and see what comes out. So yeah, it's like I said, it's one of those things. You need domain knowledge to get closer to your point, but you also have to be aware that once you bring in your bias, you have to be aware of consequences.
Okay. And my other question was about the loss function for the model. So how would you shape that differently based on some of the models that you're creating and the data that you're working with?
So I'm trying to think that I'm trying to think if I've used anything but the mean squared error. I don't know if I have, but like I said, it's one of those things where each loss function, same with the optimizer, same with all of that stuff. You just have to know what it's doing, at least have some knowledge. You don't need to know the math behind all of it, but just some knowledge and what it's best for. If I'm doing a classification where I just hold wins or losses, I'm not building the model I'm building now because there's better ways to get yes or no. I don't need negative numbers. I only need 1 and 0. So you take that into account. Okay, what's the best activation function? What's the best loss function? Things like that. So it's really knowing what you want to get and then going out and reading the documentation. Okay, what's going on here? Why is this doing this? Why is this doing that? And then deciding from there. But there's really no, there's some mostly the way I have it set up will match most of the general intro models that they show. I think one of the most famous ones is guessing the price of a house in Boston.
Yeah.
So if you look at that, you'll see, okay, this is a regression. I have an infinite number of output. The value can be, 0 to whatever. And if that matches what you're doing, okay, let's use the same thing. Let's see how it works for me, and then you can do some variations from there. But it's really what you're trying to do.
Okay. That makes sense. Thank you.
Yep. If you guys are interested, like Google DeepMind has awesome articles, blog posts all the time. If you're into gaming, they've got they created a new reinforcement, so a new Q learning class. So Q learning is reinforcement learning. They added a neural network, made it DQN. They're now at, I'm not sure what the initials are now, but it's like a double deep Q network where they've added some short-term, long-term memory, and they actually were able to beat all the Atari games, like at a superhuman level. So that's really cool to get into reinforcement learning. That's DeepMind. OpenAI has a bunch of libraries that encapsulate different worlds to train your model on. So OpenAI, Google, those are great. Facebook has some really cool stuff coming out of things they're doing. Personally, I think it's more for their company. So it's more ad-based, more suggestion-based, filtering, things like that are interesting. I'm not necessarily into that stuff, so I don't follow them too much. Like I said, they're doing, so they've got some pretty cool stuff. So those are places that I'd look if you're just like interested in general machine learning. There's a ton of natural language processing coming out. I know Wells is into user feedback. So if you go on and you leave a really sassy review for somebody, they can see, okay, this person is upset, this person's happy, whatever. They can do, I can't think what it's called, your emotion. They can say this section's good, this section's bad. So a lot of the NLP stuff is with that, and that I think is really cool. But it's really just kind of look around till you find something you like, and then there's really smart people out there trying to solve those problems.
I've seen something similar with the Yelp review where they were classifying that into either like positive or negative reviews.
Mm-hmm. Yeah, and so I think the idea behind that is if you've got 10,000 reviews coming in, you can say, give me the 10 best, 10 worst. I don't care about the middle. There's one thing I've noticed. So because I'm on the machine learning side and my brain works this way, I always find that stuff cool, but you can't ignore the emotional side. So when you automate a bunch of that stuff, you have to be aware how it affects people. So they had, I'm not sure who it was, maybe Google. They would they did some image detection stuff, and they showed one of the concentration camps as a playground because it had a fence on it. So on the engineer side of me, like, that's pretty cool. They could pick that up. On the human side, I'm like, oh, that's not ideal. You have to be careful of that stuff. So there's a lot of that I think, I'm not sure what the breakdown of this group is, but from an engineering mind, whenever you do a model, you have to think about stuff like that. Like Amazon, they didn't hire women. That's not good. You have to think of that versus, oh, that's kind of cool. Because a lot of the problems I think that you'll see with Facebook's the hot one that everyone hates right now. But engineering wise, it's right. It makes sense. But that's not always like truly right. With the Cambridge Analytical stuff, they were extremely good at convincing people to do stuff. So from engineering, that's successful. But from the human side, it's not, because they stole data, they did all this other stuff. So that's kind of what I'm interested in, to like just how people react to machines making decisions without humans involved, because they can kind of go haywire pretty quick. So if you guys have any other questions or anything you guys are looking into, or anything else to bring up?
Yeah, I have a question. I'm like a big sports fan, you know. So and then these like these NCAA teams like change vastly over year to year. Is there like a certain weight you use for like more recent data than others, or is there?
So, I have a buddy that played at UNI, and he cared more about like the human side, like the athlete side of it. So for me, it was just home versus away. I didn't care. I figured enough data would round out the human element. He was along the point of, if I am in Iowa City tonight and tomorrow I got to be in Kansas City, I'm not playing well. I'm still tired, or, stuff like that. So there are obviously things you have to be aware of. I kind of went to a game's a game. So for me, I didn't care about teams. I didn't care about years so much. I just wanted the games. But if you were to take this and there was a ton of money involved, you would absolutely have to take into account a lot of those things. So for college basketball, one and done. That vastly changes teams. You need to be aware of that, and then you just have to basically check the data to see if it actually matters. Because it seems like when they brought one and done back, that Kentucky got really good. They won a lot of games. When it came to the tournament, they still needed seniors. I have no idea how to model that. And I guess that goes into something, if you watch the videos on Facebook, they talk about feature selection. So for me, I just did the numbers. I didn't worry about all that stuff. But if you could come up with a feature that you could feed to your model that would take into account that, you'd be vastly ahead of what I can do. So there's always stuff like that to think about. One funny one that, so James Harden, because I think they play tonight, he always played worse in countries or in cities with really good adult entertainment. So they found teams that had a fantastic nightlife, and he was terrible, assuming he stayed out all night. J.R. Smith was the same way. He was terrible on Sunday games because he partied too hard. So there's stuff like that. If you could model the human element, you'd have a fantastic model. And same with, I try to think of how to do how previous games affected you. So if you play a really hard game on Tuesday, are you going to be good on Friday? And how that worked out. And it's one of those things where once you have all the data, you just sit there and mess around with it for hours on end and see what you can come up with it. But it's one of those things, you're never going to be able to model your star player breaking up with his girlfriend and not wanting to play basketball. That's always going to come back and get you. One thing that I wish I had accounted for, but I didn't, last year, UNC's point guard got hurt. So all of their numbers were terrible. But he came back and was killing. So all of my predictions for UNC were bad for like 3 weeks because all my data was a not good team. And all of a sudden their star player comes back and they start winning. So there's always things like that when I see that number, I have to know that's not a good number because it's not reflecting real life.
Thank you.
You guys have anything else? What's the major breakdown for you guys, for all of you? Is it mostly computer stuff or is it pretty sporadic?
I think the majority of us are comp sci related.
Okay.
Yeah. Yeah. Yeah, thanks so much for giving the talk. This was really cool.
Yeah, like I said, once it's in person, I can bring up my Raspberry Pi and show a couple projects.
We will definitely let you know when things start opening back up.
Yeah, that talk's tough to give, not in person, because it's hard to project what the Raspberry Pi is seeing. And when it's hooked up directly to the device, you can see what the camera sees. But if you are remote desktop into it, or if I even share my monitor, you guys can't see it because they pipe directly to the output. Anyway, so yeah, there's a Raspberry Pi talk. And I asked in, we have a GDE Slack group. I told them to reach out to you if anyone wants to do talks with you guys. Like I said, there's some people do some pretty cool projects. So I'll let you know if anyone gets back to you. Like I said, I posted the group, so if anyone's into doing talks, I'll let you know.
That's awesome. Here, I'm going to stop recording.